So this is kind of a continuation of previous talk for most of you have been here. So graph was, the last push we did for graph, introducing graph in Mathematica was in version 8. And essentially what we try to do is to build, a first-class citizen object in the system which work as anything else. And I think we succeeded, and in the version 9, what we try to do is to take a vertical approach, pick a social network or a topic and, try to see how graph apply to the area and provide the functionality. And also there, I think it was quite successful. We brought a set of functionality, quite interesting, and the feedback was positive. So in version 10, what we did essentially is more to take an horizontal approach. So what essentially we did is to try to, extend the coverage we have. The first thing we did is first, in terms of usability, try to improve, the integration, interactivity, and performance in the system. So that's kind of what's happened transparently without you noticing, but you just notice that everything worked more nicely. So the whole aim, in long term is to just that it magically do what you want. And in the same spirit of Mathematica and all other areas, we kind of added new functionality. So what we focused essentially was on paths, cycles, and we introduced also visualization I'm going to talk about, and hopefully we'll also have polynomial and other more mathematical-based functionality for some of the people who like them. So let's first talk about integration. As you know, before graph in the kernel, we had two essential packages which were doing graph theory, combinatoric and graph utilities. So combinatoric is a big package. Beside graph, it has combinatoric functionality. So the long-term plan is to kind of make all those packages obsolete and have all the functionality in the kernel. But that takes time. That takes time for you user to actually adapt and change and update your package. So we go slowly and take our time. So in this release, the first thing we did is that we managed to make graph utility obsolete for Mathematica. So what I mean is that all the functionality in graph utility is actually currently or will be in version 10 kernel. So, and what we did to actually ease the transition is that we built a compatibility page. If it managed to open, right? So we have a nice compatibility page. We kind of show you, the graph utility package, functions, and the corresponding building function in Mathematica. Oh, yes, thank you. That good? Much better? Okay, great. Okay, so we have a list of functions, graph utility functions. We kind of went through the whole package and included a full list. So that kind of make it easy if you make a transition or want to learn. And they are close related, it's not too magic. So the next thing we did actually is to go one step further, which requires actually much work, is to actually go to the documentation of the package and actually show you how you are going to do the transition, which is kind of first time we do that actually in the system, and it's a lot of work. And the package sometimes is not even documented, but we kind of try to make it easy for you to see how you were using it before, what's the new functionality. So that's kind of the transition we do for graph utilities. And we hope that in the next future version, we are going to do the same for combinatorica, which include more than graph theory, so essentially. Okay, so let me get back to my talk here. Oops, not that one. Right. So that's in terms of usability and integration with graph utilities. So the next thing we did actually, also you probably notice in terms of performance, is that we improved the interactivity. The visual interactivity in the system. So earlier, some people who actually like to dig inside Mathematica and look at the expression. When you generate a graph, usually if you do a show and you look at actually the graphic or the expression inside was a really complex expression with some magical symbol and stuff. So what we try to do is to improve that. And that whole magic was essentially is that the front end, the rendering was high quality rendering. So the front end had to do a lot of computations. And in this version, what we did is that we tried to simplify it and make it quite simple, but keep the high-quality rendering available to you. So as you can see, in this case, for a graph 1 to 2, if you compare it with version 9, you see that the expression changed, but you still get the same high-quality rendering, but more efficient, and it'll be more faster. And Eric actually pointed me out that, usually when he starts his notebook, most of the time he doesn't have, or when he doesn't have a kernel available, he cannot see the graph. So these are kind of usability experience we try to improve. And hopefully in this version, when you open your notebook, you will not actually need the kernel. You actually just get your graphic rendering. The other thing we did essentially is also to improve the rendering of large graphs. So essentially, when you have a large graph, so by large I mean thousands of vertices in our term, when you decide to render the graph, when you reach thousands of vertices, essentially a point or a vertex is roughly a point. It's small enough that you cannot make any distinction. In earlier version, we were still trying to draw it with high quality, circle or disk or anything like that. So what we did is that we improved the rendering, that transparently for you, we kind of try to understand the resolution of your system or other different parameters in your system and figure out when you have to actually render a disk or something of high quality than just a point. And we have several cutoffs. And one advantage of that is that the rendering actually is more, the performance actually is much better in terms of rendering on the front-end side as well as on the kernel side when it's about drawing a graph. So, and you can, see benchmark. But hopefully that will just work transparently for you and you will actually more enjoy using graphs. So that's kind of usability and, interactivity. And the last part in terms of usability I want to talk about is always the performance improvement. So we continue to improve the whole performance in the system. As much as we can, we improve the algorithm, we make them multi-threaded to get, all the power and deliver, the most and the fastest functionality and software. And currently, I can claim that we're actually the fastest and the best in the market in terms of graph and networks, at least. Okay. So now let's talk about actually what is new. I mean, what you are going to see and what you are going to, advertise and kind of motivate you to actually buy more Mathematica. So one of the first things we did is that we focus on pattern cycles. A lot of people, and Stack Exchange and feedback, people wanted stuff about graph, pattern cycles. So what we did is that we introduced a suite or a set of functionality related to graph and pattern cycles. So the first one is vertex-independent path. So essentially, if you give him 2 vertices here, 3 and 4, you can ask him to find you 5 independent vertex paths. So essentially, we'll give you a set of paths which doesn't intersect at a vertex. That's vertex-independent path. And he gave you a list. In this case, we don't, we generate a set, the pair of vertices. And the edge-independent paths, as you can imagine, is the same. He gives you a set of paths which doesn't intersect, share common edges, but they can share a common vertex. And the last function in this set is find path, which essentially find you all possible paths between 2 points in your graph. You can put a threshold to limit the number of paths, or you can tell him, give me all paths. So as you can imagine, in some cases, it can be huge and difficult to represent in the system, so that's up to the limitation of your system. We try to manage it as much as we can. And the example below is just if you pick a polyhedra, a circle ball from polyhedron data, you can actually compute all the paths and actually visualize it nicely. Let me get to high resolution. Yeah. So here you get, pardon?
Can you scroll the graphic higher up? Maybe just make your notebook smaller. Graphics are yeah, press enter a few times.
Oh, right. Thank you. That's a great idea. So essentially, you build a graph from a polyhedron, from a soccer ball, and then you can, pick 2 points and then find all possible paths and just visualize it. So, kind of nice and funny things to do. So that's, path. So now in Cycle, actually, what we did is that we introduced a suite of functionality. So essentially, also Cycle are similar to Path, essentially, the Path. But the main thing is that with Cycle, you can actually generate a basis. Depending on the way you can see it as a, a vector space and do some basic, algebra on it. But essentially, you can generate a basis which kind of help you to express or to do some computation on path. So one of the first functions we introduced is Adjacency Matrix, which essentially gives you a matrix which actually kind of an encoding of the basis of your cycle. So these are the fundamental elements of your basis. So if you just combine it with edge lists, this kind of gives you the basic cycle you have for your graph. So if you do a linear combination of these cycles, you will get all possible cycles. So that's kind of the basis. And this is just a basic code to show you how to compute all possible cycles. So this is just a sample example. You can go and scale it on hundreds or thousands of vertices. So the next function we introduce is find fundamental cycles. So fundamental cycles are actually essentially a basis, but the only difference is that it comes from a spanning tree. So, and one advantage compared to the Adjacency matrix is that this basis is always integral, and all the mathematics behind is one of the nicest bases you can have. So find fundamental cycle also give you then a basis. It returns you a list of edges. You see there. And you can use it to generate all possible cycles of your graph. So that's also another basis thing. So to make your, oops, I'm sorry about that. So to make your life easy, we also introduce find cycle. We just give you all cycles. And this example is a favorite example of Roger, which essentially, when he has to walk his dog, for some reason, you have to pick a path. So that is, if you pick a neighborhood of your house, and then you have a path where there is a back dog, you want to avoid that path when you walk your dog. So, that's a simple problem he wanted to resolve to be able to walk his dog. So if you take the neighborhood, that's a neighborhood and houses, and then the yellow one are the bad road you don't want to pick, you can ask all the possible work so that you can, walk your dog, and then you can visualize one. So every morning you can wake up, run mathematics, and pick the right road you want, so to walk your dog. So that's find cycles. So the spanning tree is the smallest tree, which can reach all possible vertices in your graph. So it's one of the most efficient functions. Actually, you can compare there. I don't have comparative here, but we did benchmark. And that we computed the spamming tree. I'm surprised that I cannot highlight it. Okay, just give me a second here, and my kernel died. Okay. So essentially, spamming tree compute a spamming tree. So this is the spamming tree essentially, and then you can highlight it. But do highlight graph. So doesn't work. I will not hold that. I will continue. So the next function we also introduce is actually transitive closure. So essentially, transitive closure and transitive reduction are roughly the same. So essentially, when you have, if you think about the graph as a relation, a relation, you have reflexive, symmetric, transitive. So transitive closure is just equivalence of, transitivity. So transitive closure is the graph such that if A is connected to B and B is connected to C, then A is connected to C. Just a basic transitivity relations. So if you construct a random graph directed, you can get the transitive closure. And it's quite useful function. And you can also do the inverse. You can find the smallest graph which have the similar transitive closure. So this is a basic example where, if you have a family tree, not really family tree, but yeah, roughly the family tree is the same. And then you can evaluate it and get, the smallest representation in your structure. Okay, so that's kind of in terms of constructors. So the next functionality we introduce is visualization of graph in 3D. most of the people ask it. We have graphic 3D, we have graph, but why not in 3D? So we introduce 3D graph. So if you generate a graph and you do graph 3D, is a constructor, it builds you the new graph, a 3D graph, essentially. It behaves like a graph. You can manipulate it, rotate it, adjust it. It's still a graph. You can do all computation on it. Right. No, in principle, it's not a different head. It's still a graph. Yes, it's evaluated to a graph. It's a same graph, just purely a graph. So it's mainly, if you think about it, just a property. Is a 3D object or not 3D object. That's essentially that. And having a 3D graph also means we need to extend all the 3D layout. So what we did, we went to all the 3D layout we have from Spring Electrical to circular embedding, and we extended it to 3D. Actually, most of them to actually high dimension, which unfortunately we cannot visualize high dimension or not yet. Or some function like random graph, when you generate a spatial graph distribution in 3 dimensions, you get directly a 3D object where the points are distributed, depending on your distribution. Here is a uniform distribution over a square box. Or you can generate a random graph and specify the dimension, and then you get a 3D object flat. Not too interesting, but it's there. So that's in terms of visualization. So what's coming more? So this is just a kind of a tiny preview. More functionality in terms of connectivity, K connectivity, vertex, edge connectivity. And we plan to actually push in terms of polynomials. People who love the basic fundamental in mathematics, as Eric, will have probably several types of graph polynomials, which will be efficient. And also what we hope is to do a push in terms of isomorphism. So we probably also introduce graph automorphism group and graph canonicalizations, which is based on the NOTI package. So there are several types of canonicalization for graphs. But this one will be one which will actually nicely match with our graph data. And definitely there are more functionality I'm not talking about here, and hope, when you get the version 10, you'll actually enjoy it. So in conclusion, what do we bring in version 10? We bring a better integration, and we keep working on that. Better interactivity and performance. New functionality about pattern cycle, tour. New constructor for graph, 3D visualization, and a flow of mathematical functionality. Future direction, we can discuss it about later. We have a lot of ideas, but we'll keep track on, working on graph, improve it, and bring more functionality, and probably do several verticals, horizontal and verticals. And I will close by just pointing you out that a couple of talks we have later on in graph and networks. There'll be a graph in finance, graph computation in finance by J-Bomb at 4. I will probably give a next talk about statistics and graph today again at 5. And tomorrow there's a talk with Eric and Stan on new development and research and application of graph data. And there'll be a social network analysis by J-Bomb and Jan. And you're all invited, and I'm sure you'll all enjoy it. Thank you.